Above the dark, open sky, a quiet scatter of stars frames a question we've carried for generations. How fast can we push a human-made craft before nature taps the brakes? Engines flare, irons whisper, sails catch light. Each hints at speed, each hides a cost. Distances don't blink, signals lag, dust becomes danger. Somewhere between ambition and limit sits a number that matters not for records, but for whether a crew can cross our own sun's neighborhood within a lifetime. Tonight, we'll approach that edge and see what makes it hard without spoiling the path ahead. If clear, down-to-earth space talk like this resonates, a gentle like and subscribe helps. Settle in. Let's find out what fast really means. Right now, Voyager 1 is moving through interstellar space at about 38,000 miles per hour, a steady glide that sounds fast in everyday life, yet runs into the scale of the cosmos. At that pace, the time to the nearest star is measured not in years, but in tens of thousands of years, roughly 70,000 for Proxima Centauri. This sets the frame. Our tools can move quickly by human standards, while space stretches the clock. The question becomes how far today's propulsion can carry us, what each system trades for speed, and why distance and energy set limits that do not bend to will. The Moon helps make the first step clear. It sits around 238,900 miles away. Apollo crews reached it in about 3 days after a maneuver called translunar injection, an engine burn that put the spacecraft on a path to the Moon at roughly 25,000 miles per hour. That is faster than any aircraft and far beyond a rifle shot. And yet, across the larger map, it is a short hop. The record for raw speed belongs to a craft that dives toward the Sunday Parker solar probe, launched in 2018, swings past Venus again and again to fall deeper into the Sun's gravity well. Each pass tightens its path. Near perihelion, the closest point to the Sun, it reaches around 430,000 miles per hour. A city-to-city trip on Earth would take seconds at that rate. Even so, the nearest star would still be thousands of years away. Speed that feels huge beside Earth shrinks in the interstellar context. A simple scale helps hold the picture. If Earth were a marble, the Moon would be a pea about a foot away. Mars at its closest would be a smaller marble, about 30 feet away. The Sun would be a beach ball, 400 feet away. And Proxima Centauri would be another beach ball, about 24,000 miles away. A span like circling Earth at the equator. These are not strict measurements, only a way to sense how separated the pieces are. Empty space is not only empty, it is spacious. Voyager 1 and Voyager 2, launched in 1977, are our most distant operating spacecraft, and a clear lesson in how to gain speed without giant engines. Voyager 1 crossed the boundary of interstellar space in 2012. Moving beyond the Sun's magnetic bubble, it is now more than 15 billion miles from Earth. A radio signal, moving at the speed of light, takes over 22 hours one way, which means a round-trip exchange takes nearly 2 days. Commands have to be planned and checked with patience. The way Voyager reached its speed is a core technique in deep space travel: gravity assist. When a spacecraft falls toward a massive planet and flies behind it, it can leave with extra speed relative to the Sun, like rolling downhill and timing the turn to leave the slope with more momentum. Nothing is violated. Energy is exchanged. The planet loses an almost unmeasurable amount of orbital energy. The spacecraft gains what it needs, and mission design turns the solar system into a set of ramps. New Horizons shows a different piece of the puzzle. It left Earth in 2006, faster than any previous craft at launch, about 36,000 miles per hour, crossing the Moon's orbit in roughly 9 hours. That quick start did not make the journey short. Pluto, still within the Sun's family, required about 9.5 years to reach. Speed at launch helps, but the distance is unforgiving. The physics that guide all of this sit on a simple base. There is no air in space to push against, no track to grip. A spacecraft changes its speed by throwing mass in the other direction. This is Newton's third law made practical. Push something backward, you move forward. Chemical rockets do this by burning propellant and pushing hot gases out the nozzle at high speed. They are reliable and powerful, but they demand a lot of propellant. For a large rocket, most of the weight at liftoff is fuel, and the structure that holds it. A large part of that fuel is burned just to lift the rest of the fuel. This loop is captured by the rocket equation, which relates the change in speed you can get to how fast the exhaust leaves and how much propellant you carry. It is a firm rule, not a suggestion. Electric propulsion tries a different trade. Ion engines use electricity often from solar panels to accelerate charged atoms to very high exhaust speeds. The push at any moment is gentle. So gentle, you could balance it on paper, but the engine can run for months or years. Because the exhaust speed is high, the total propellant needed for a given change in velocity is far lower than with chemical rockets. NASA's Dawn spacecraft used ion propulsion to go to Vesta and then to Ceres, reshaping a mission plan that would have been impossible with conventional burns. The price is time. Ion engines are marathon runners. They build speed slowly and work best when you have the patience to let small pushes add up. Human speed marks another benchmark. The crew of Apollo 10, Tom Stafford, John Young, and Eugene Cernan reached about 24,791 miles per hour during their return from the Moon. For a moment, they were moving about 7 miles each second relative to Earth's surface. If you point that number at the nearest star, the scale speaks again. At that rate, the trip would take on the order of 100,000 years. To bring it into a single human life, even a long one, you would need to multiply that speed by a few thousand, a jump that demands a new class of propulsion and new ways to handle heat, radiation, and collision risk. Light itself can push. Solar sails take advantage of photon momentum. A photon has no mass, but carries momentum, and when it reflects off a mirror, it transfers a tiny force. Spread a thin, reflective sheet over a large area and sunlight becomes a steady pressure. The Japanese Ikaros mission proved controlled solar sailing in deep space, and the light sail projects demonstrated sustained flight using sunlight. The limits show up with distance. Solar intensity drops with the square of the distance from the Sun. So by Jupiter, the push is about 1/25 of what it is near Earth. To keep accelerating, sails must be very large and very light, strong enough to resist tearing and to hold shape under a soft, constant push. Concepts call for structures miles across, made from materials thinner than paper. The engineering is difficult, and even with success, the timescale to reach another star would be measured in decades to centuries for very small craft. One proposal seeks to sidestep the Sun's fading light by supplying the push from Earth. Breakthrough Starshot outlines tiny spacecraft gram-scale chips with cameras and sensors attached to very small, highly reflective sails. A ground-based laser array would shine on the sail with immense power for a short period, pushing the craft to a fraction of light speed, perhaps around 20%. At that rate, a flyby of Proxima Centauri could happen in about 20 years. The idea is simple to state and daunting to build. The sail must survive a fierce laser push without tearing or heating too much. The beam must stay on the target for minutes across long distances through the atmosphere. The power required is on the scale of many large power plants operating together. The vehicle must navigate and communicate across years with minimal mass and no chance to break at the destination. It is a bold research path, and it highlights how much infrastructure would be needed to push even very small craft to interstellar speeds. Nuclear propulsion offers nearer-term gains within the solar system and a possible bridge to faster uncrewed probes. One early concept, Project Orion, proposed riding the shockwaves from a series of nuclear explosions behind a strong pusher plate with shock absorbers. The physics support significant performance. In principle, such a system could reach a few % of light speed, cutting interstellar travel to centuries rather than millennia. The practical and environmental issues are obvious, from testing to launch safety to treaty limits, and the concept was set aside. More modest nuclear systems are under study. Nuclear thermal rockets would use a reactor to heat a propellant like hydrogen and expel it, doubling the exhaust speed compared to many chemical systems. Nuclear electric designs would use a compact reactor to power ion engines, combining high exhaust speed with steady, long-duration thrust. These approaches could shorten trips to Mars from something like 9 months to a few months, which matters for crew health, logistics, and mission risk. They do not turn an interstellar cruise into a short voyage. They make regional travel more practical. Relativity adds another layer, but at our reachable speeds the effects are small. Time dilation, the slowing of time for a moving clock compared to one at rest, shows up in satellite systems. GPS satellites move at about 8,700 miles per hour and sit higher in Earth's gravity field than we do on the ground. Their onboard clocks drift by tens of microseconds per day from both motion and gravity effects. The system corrects for this, or position fixes would fail. This confirms Einstein's theory in daily use, while also reminding us that to get dramatic time dilation, you need speeds close to light. Our current craft are far from that regime. Speed does not live alone in mission planning. Planets move, the sun pulls. Launches aim not at today's target, but at where that target will be months from now. For Mars, good launch periods windows arrive roughly every 26 months when the geometry lines up. Miss a window, and the energy cost rises, or the wait begins. Interplanetary travel is an exercise in intercepting a moving object while you are also moving, all inside a system where gravity is always at work. Trajectories are designed with care, small course corrections are planned, and margins are kept for the unexpected. The math behind those paths folds in the pull of the sun and the nudges from large planets. Jupiter's gravity is strong enough to change trajectories for missions that never go near it. Even Saturn or Neptune can matter in small, predictable ways over long times. A tiny angular error at departure can grow into a large miss many months later. Navigation teams track the spacecraft, compare its radio signal against models, and plan burns measured in fractions of a degree and small amounts of speed to stay on track. These are gentle, precise moves, and they matter as much as the big burns. Cassini's journey to Saturn shows how speed, timing, and fuel come together. Launched in 1997, it did not take a straight, fast shot. It used gravity assists to gain energy without hauling impossible propellant. The path swung by Venus twice, then Earth, then Jupiter, each flyby tuned so the spacecraft departed with the right aim and speed. Arriving minutes early or late can shift the exit path, so navigation and timing had to be exact. After nearly 7 years, Cassini reached Saturn in 2004. To stay, it had to slow relative to the planet. The main engine burned for about 96 minutes to drop speed enough for capture, with orientation and timing set to tight limits. Too little or too much, and the result would be a miss, an impact, or an orbit that did not fit the science plan. This operating pattern bank energy with gravity assists, then lock arrival speed to science needs, became a template for later deep space missions. Europa sits beneath Jupiter's radiation belts, its ice shell hiding a global ocean likely kept liquid by tidal heating. The distance is modest on cosmic scales, but still decisive for design. At favorable alignment, Jupiter remains about 365 million miles from Earth. Applying the same template, Europa Clipper, launched in 2024, uses a gravity assist trajectory to save propellant and manage arrival speed before entering Jupiter orbit. It will then make repeated close passes of Europa to collect radar maps, ice thickness profiles, plume sampling, and magnetic signatures that point to a salty, conductive ocean. It does not land. The surface is bitterly cold, mechanically tough, and bathed in intense radiation. Surviving there for long demands heavy shielding, robust power, and systems that function after months of energetic particle hits. Finding signs that point to life creates new requirements. A clear detection from orbit, organic molecules linked to ocean material, or a chemical imbalance that suggests active processes would push toward the next step, touch the surface, maybe drill through miles of ice, and sample the water below. Each stage multiplies time. Design, testing, and launch are measured in years. Cruise adds more years. Landing and drilling add years again. People who write the proposal may not see the data. Students who start their careers on the project may be teaching when first results arrive. This is not a failure. It is the cadence set by distance, power limits, radiation, and the speed we can reach with real engines and real budgets. Communication speed adds a separate limit. Radio waves and light move at about 186,000 miles per second, the fastest speed there is. Across the solar system, even that speed leaves long gaps. When Earth and Mars are well placed, a one-way signal can take around 3 minutes. When they are far apart, it can take over 20 minutes. You cannot joystick a rover under those conditions. Entry, descent, and landing sequences run on software that was tested on Earth, verified in simulation, and then given the authority to act. The 7 minutes of terror for Perseverance were already over by the time confirmation reached mission control. The same pattern applies farther out. A command to a spacecraft near Jupiter can take tens of minutes to arrive one way. To Saturn, roughly an hour and more. At Pluto, several hours. Exploration turns into careful planning, onboard autonomy, and fault protection systems that let a craft detect problems and move to a safe state without waiting for instructions. Distance also changes how we think about power. Solar energy thins with the square of distance. At Jupiter, you get about 1/25th of the sunlight you get at Earth, and at Saturn, about 1/100th. Rovers and orbiters far from the Sun need nuclear power sources, or very large arrays, and both choices add mass. More mass means more push at launch. More push means more propellant. The chain loops back to propulsion every time. Energy budgets help make the scale real. The space shuttle needed on the order of 3.5 million pounds of propellant to reach low Earth orbit. The chemical bonds in that propellant released energy roughly comparable to 10 trillion calories, enough to feed a large city for a year if you could turn rocket flame into food, which you cannot. Despite the size of that number, the result was only a few hundred miles of altitude and about 17,500 miles per hour in orbit. To leave Earth for the Moon, the Saturn V pushed through about 6.2 million pounds of propellant in minutes. The power involved was huge and brief. These numbers are not there to impress. They frame why going a little faster costs a lot more. Scale the target to interstellar speed, and the numbers climb beyond daily intuition. At 1% of light speed, about 6.7 million miles per hour, a 1-ton craft would carry kinetic energy on the order of 4.5 times 10, 14 joules. That is similar to 100 megatons of TNT. Increase the mass to something that can support people for years, and the energy requirement grows with it. You still need to slow down at the end if stopping matters. Every bit of energy you add to speed outbound has to be managed on arrival, unless the mission is a flyby. If you must carry the fuel for both acceleration and braking, the totals swell further. The rocket equation explains why. The change in speed you can achieve, called delta V, is the exhaust speed multiplied by the natural log of the ratio between the initial mass and the final mass. That Ln term is the core. Mass in the numerator includes propellant, tanks, engines, structure, shielding, and payload. Mass in the denominator is what remains after the propellant is gone. Because the function is logarithmic, small gains in delta V are cheap at first and expensive later. Doubling delta V can demand many times more propellant if exhaust speed stays the same. This is why engineers chase higher exhaust velocity, lighter tanks, and smarter trajectories. It is also why plans that look fine on paper at small scales explode in mass when you scale them to human-rated interstellar speeds. Thought experiments with near-perfect engines show the same pressure. Even if you could convert matter and antimatter to energy with extreme efficiency, a small payload still needs a large mass of reaction material to reach a tenth of light speed and an equally large mass to slow down. Add tanks, shielding, guidance, and life support, and the initial mass can rise by factors that make the stack hard to build, hard to launch, and hard to assemble in orbit. Each added kilogram needs more propellant to move, which adds more kilograms, which needs more propellant again. Speed in low Earth orbit helps show the difference between moving fast and going somewhere. The International Space Station circles Earth at about 17,500 miles per hour, lapping the planet roughly once every 90 minutes. Crews see many sunrises and sunsets per day. A small chip of debris can be dangerous at that speed, yet the station is still bound to Earth. To climb out, you need extra delta V to raise the orbit, and then more to head to the Moon, Mars, or beyond. Hubble travels at a similar speed while doing a different job. Its task is to gather light, not cover distance. By looking with long exposure times and sensitive instruments, Hubble can study galaxies billions of light years away without moving more than a few hundred miles above Earth. This approach trades travel for vision. The James Webb Space Telescope extends that trade by sitting near the Sun-Earth L2 point, about 1 million miles away on the night side. A Lagrange point is a place where the gravity from the Sun and Earth plus the motion of the spacecraft balance out, allowing it to keep a steady position relative to Earth with small adjustments. Webb reached L2 in about a month, at a gentle cruise. It needs stability and cold temperatures, not speed. From there, it can watch faint, distant light that started its trip when the first galaxies were forming. Observation can carry as far, Yet some questions need local work. Confirming life in Europa's ocean requires sampling that ocean. Understanding ancient climate on Mars benefits from drilling rock layers and returning cores. Learning what drives chemistry under the clouds of Venus needs instruments that can survive heat and pressure at the surface. These tasks ask for arrival with the right tools, long-lived systems, and enough data bandwidth to send results home over long delays. Speed matters only to the point that a mission can be done within planning horizons and careers. Beyond that point, power, shielding, and reliability dominate. Designers stretch what time and fuel allow with several linked strategies. Trajectories are chosen to maximize gravity assists while keeping arrival speeds manageable. Launch windows are timed carefully, so planets are in the right places. For some missions, the daily window is narrowed to minutes. Small burns done early can save much larger burns later by trimming angles and timing. Missions accept trade-offs between cruise time and capture requirements. Going faster to a giant planet can make it too expensive to slow down for orbit, so the path may loop past inner planets first to add energy in the right direction without carrying a mountain of propellant. The Galileo flight to Jupiter used Venus and Earth flybys for this reason. The Messenger mission to Mercury took a long, stepped route, 1 Earth flyby, 2 of Venus, and 3 of Mercury, to bleed off speed so that a modest engine could achieve orbit around a small, hot planet close to the Sunday. These tools work within the Sun's family because there are massive bodies to borrow from and sunlight or nuclear systems to power instruments. Interstellar space is different. Between here and the nearest star, there are no planets to bend your path and no easy refueling stops. A craft must carry or harvest all it needs. Laser-pushed sails change the architecture by putting the power source at home, but they push only tiny payloads today and do not help with braking at the target unless another beam system waits there. Nuclear electric engines can run for long durations and offer higher exhaust speeds than chemical rockets. Yet powering them at interstellar levels points to reactors, radiators, and shielding that add mass. Each option drags on the same constraints: energy available, mass to move, heat to reject, and time in transit. Communication and autonomy scale with distance as well. Long one-way delays force planners to give spacecraft more decision authority. Fault detection, isolation, and recovery routines watch for sensor outliers, power drops, and temperature excursions, and then switch modes or reconfigure hardware without asking. Science operations rely on onboard targeting, compression, and prioritization to send the most important bits first over narrow links. As missions push outward, software becomes as central as engines because it keeps the craft productive between commands and protects it when conditions shift. Radiation and dust shape the envelope for high-speed flight. Energetic particles from the sun and from outside the solar system can flip bits in memory, damage detectors, and slowly degrade materials. Spacecraft use error-correcting memory, watchdog timers, and shielding to survive. At higher interplanetary speeds, micrometeoroids carry enough energy to erode surfaces or puncture systems, so designers consider Whipple shields, thin sacrificial layers that spread out impacts before they reach the main hull. These protections add thickness and weight feeds back into propulsion. Power systems trace similar lines. Solar arrays work well near Earth and out to Mars with careful sizing. Beyond that, their area grows large and their structure becomes heavy. Radioisotope power systems deliver steady electricity for decades, enabling missions like Voyager, Cassini's Huygens probe to Titan, and New Horizons. Stockpiles of suitable isotopes, heat management, and converter efficiency set practical limits. Advanced nuclear systems under study seek higher power for electric propulsion or surface work on distant moons. Each watt you carry has to be launched, supported thermally, and managed over years. Navigation across tens of millions of miles relies on precise tracking. Teams measure Doppler shifts and timing in radio signals to estimate velocity and range. Star trackers fix attitude by comparing camera images to catalogs. Tiny trajectory correction maneuvers, often just seconds of thrust, trim the path to hit a flyby altitude or an entry corridor. Errors early are cheap to correct. Errors late can be costly. Planning builds in contingencies for solar storms that can introduce noise into communications, or for safe mode events that pause operations until ground teams can assess the situation. Human travel adds layers. Life support needs air, water, food, and waste handling for months to years, plus shielding for radiation and room to sleep and work. Every kilogram devoted to crew systems is a kilogram not available for fuel, cargo, or shielding. Faster trips to Mars using nuclear thermal stages could cut exposure time to radiation and microgravity. The trade then shifts to reactor mass, engine reliability, and ground testing to clear safety gates. For farther destinations, cruise durations stretch, and reliability over long times becomes a primary design driver. Redundancy, fault tolerance, and maintainability move to the center of the plan. When designers examine concepts like generation ships, they fold social and biological continuity into the same charts that track mass and power. Closed-loop life support must recycle water and air for decades. Agriculture has to work in artificial light or under constrained sunlight. Medical care must be robust enough to handle emergencies without rapid evacuation. Governance and education must keep the mission's critical skills alive. These are not speculative add-ons. They become core systems when travel spans many human lives. Alternative payload strategies try to reduce the mass that must be accelerated. Tiny probes moved by beamed energy cut the onboard power requirement. Frozen embryo concepts replace adult crews with small biological payloads and long-life caretaking systems. Digital blueprints sent ahead for assembly by autonomous factories would shift the launch burden from bodies to information. Each scheme moves the mass around. None removes the need for reliable power, precise navigation, and durable hardware over long spans. Inside the solar system, these limits still leave room for steady progress. Faster communications relays at Mars ease bandwidth limits for rovers and sample return craft. Surface reactors, or large arrays, enable drilling and chemistry on icy moons. Smarter autonomy lets landers handle hazards without minute-by-minute control. Higher ISP engines with higher exhaust speed, let orbiters tour multiple moons without exhausting their propellant. Launch vehicles with better performance reduce the number of assembly steps in Earth orbit for complex payloads. Each improvement eats into the margins that once made a mission impossible and turns it into a problem of integration, testing, and scheduling. Radiation in space ties directly to speed and distance. Near Earth, the planet's magnetic field bends many charged particles away, so crews get only a fraction of what deep space delivers. Even so, the International Space Station sees about 10 times the dose we get on the ground, which sets practical limits on how long people should stay. Step outside this shield and the numbers climb. Solar storms throw out bursts of energetic particles. High-energy cosmic rays, atomic nuclei moving near light speed, come from supernovas and other extreme sources. On a months-long trip to Mars, astronauts are exposed the whole way. The expected dose raises lifetime cancer risk in a way space agencies track carefully with models, sensors, and medical rules. It is tolerated for a single Mars mission, but it is not gentle. Stretch the travel time to decades and the problem changes shape. Total dose adds up, and protecting people starts to demand thick shielding. Water works well. So does polyethylene and other hydrogen-rich material. Lead stops X-rays, but for the highest energy particles, it can make harmful secondaries, so designers often favor lighter elements. No matter the choice, mass climbs quickly. Extra shielding means extra tons. Extra tons mean more propellant at launch or more powerful stages. The loop leads back to propulsion budgets and the same math that ties speed to mass. At very high cruise speeds, a new effect appears. Interstellar space contains thin gas, mostly hydrogen, with a few atoms per cubic centimeter. At walking speeds, it is nothing. At a tenth of light speed, those atoms hit like radiation and can create showers of secondary particles inside a hull. Push to higher fractions, and the dose from the gas itself becomes a hazard, even if you manage cosmic rays. The faster the ship, the thicker the shield you need. Thick shields drive up mass, and mass pushes against acceleration and range. Designers have explored electromagnetic shielding instead of, or in addition to mass. Strong magnetic fields, like Earth's, can bend charged particles away from sensitive areas. In principle, this can protect a habitat, but the field strengths are large, and the coils need power and cooling. Superconductors help, but must stay cold and intact. Every pound of coil and radiator joins the tally that a rocket must move. Navigation at high speed is its own discipline. On Earth, a wrong turn costs minutes. In space, a change in direction costs propellant and can be expensive if you are moving fast. A course correction is a change in your velocity vector, not just its size. At 1/10 the speed of light, even a tiny angle shift represents a very large sideways speed. You pay for that with fuel, or with long, planned interactions with gravity fields, if any are available. An interstellar craft cannot afford repeated trial and error steering. The aim must be precise before it leaves. Star positions, their motion across the sky, and the pull from nearby objects over years all go into the initial solution. Guidance uses star trackers, gyroscopes, and pulsar timing to hold attitude and verify position. Small thrusters trim the path early when tiny burns matter most. Wait too long, and the energy needed to fix a small angular error can exceed what the mission can carry. The dust problem grows with speed too. Interstellar grains are sparse, but a single sand-sized particle at 20% of light speed carries energy like an explosive fragment. A larger pebble is worse. Designs protect the forward direction with sacrificial layers, often called a Whipple shield, where a thin outer sheet forces an incoming particle to vaporize and spread out before it hits the main wall. Forward tanks of water or ice can double as impact absorbers. Magnetic fields can deflect charged dust, though much interstellar dust is neutral. Radar and LiDAR cannot help at a long distance because closing speeds are too high. The result is that armor must be assumed, and that armor adds mass. The trade is unavoidable. Shield weight versus risk. Cost scales with mass and complexity. Large programs we know Apollo, the space station, a flagship telescope, live in the tens to hundreds of billions of dollars over many years and many suppliers. Interstellar hardware points toward larger numbers because of long operational life, major launch stacks, deep space power, and new propulsion systems. A craft that carries its own shielding, reactors, engines, spares, and a habitat would require funding beyond any current single project. Governments plan on election cycles and decadal surveys. Agencies commit for decades at most. Private funding can be bold, but still seeks timelines and milestones that fit within a generation. Concepts that need centuries of upkeep, logistics, and training ask for an economic base that likely includes space industry on a solar system scale, mining, refining, power generation, and shipyards beyond Earth orbit. Some argue that a broad space economy could change the math. If metal, water, and fuel are processed from asteroids and icy moons, if power comes from large solar or nuclear facilities built in space, if vehicles are assembled without lifting every bolt from Earth, then energy and mass per dollar could improve. Even then, leadership and social focus must select such missions over others. Building communications networks between planets, habitats, and factories may take priority for a long time. The choice to move beyond the Sun's family with large payloads would have to compete with many nearer goals. Advanced propulsion ideas try to bend the limits. Antimatter looks ultimate on paper because matter and antimatter convert their full mass to energy when they meet. In practice, we can make only tiny amounts in accelerators at great cost. Storing it requires trapping charged antiparticles in electromagnetic bottles so they never touch normal matter. Any failure dumps energy at once. A system that carries meaningful amounts would need robust fields, perfect vacuum, and fault-tolerant control. Engineers have built penning traps for research, but scaling to grams is far beyond today's devices. The safety case is demanding because the stored energy is so dense. Fusion drives are nearer in spirit to machines we already study. Fusion joins light nuclei into heavier ones and releases energy, as in stars. We have made fusion in short bursts and in weapons, and we are approaching net energy in experimental reactors on Earth. Turning fusion into a rocket means creating a reaction chamber that can ignite fuel pellets or sustain a plasma, then direct part of the energy out of a nozzle as high-speed exhaust. Common fuel ideas include deuterium and helium-3. Helium-3 is rare on Earth, so concepts imagine collecting it from the outer planets, especially Jupiter, or from the Moon in tiny trace amounts. Exhaust speeds, in the few percent of light speed, are often cited for optimistic designs that would shrink travel times within the solar system and make uncrewed interstellar probes more plausible. The hardware still needs large radiators to reject heat, strong magnetic fields to contain plasma, and reliable systems that can operate for years. Beamed energy propulsion shifts where the heavy equipment lives. If you build an array of lasers or microwaves near Earth or near the Sun, you can push a sail without the craft carrying the power source for acceleration. Breakthrough Starshot adopted this approach for gram-scale probes and aims for about 20% of light speed using a powerful, short laser pulse. The sail must not tear, melt, or curl. The beam must stay on target through the atmosphere and over long distances as the craft accelerates away. After the push, the probe coasts. Braking at the destination would need another beam there, or a different method such as a magnetic or photon sail interacting with the destination star's wind and light. For large payloads, beamed power would require arrays orders of magnitude bigger, with phase control over millions of emitters. Magnetic sails work differently than light sails. A loop of superconducting wire carries current and creates a large magnetic bubble around the craft. Charged particles in the solar wind or interstellar medium interact with that bubble and can transfer momentum. The force is gentle but continuous, and in theory, a magnetic sail can also break against a star's wind at the far end. The loop must stay superconducting, which means keeping it cold and intact. Micrometeoroids, radiation, and thermal cycles challenge that. The initial energy to charge the loop and the structure to hold it add mass that engines must first move out of Earth's gravity well. The Bussard ramjet tries to avoid carrying fuel by collecting interstellar hydrogen with a huge magnetic funnel, compressing it to fusion, and expelling the products. The interstellar medium is too thin for easy intake, so the scoop must be enormous. At low speeds, drag from the scoop can be larger than the thrust. At high speeds, fusion ignition becomes a physics and engineering problem. Variants propose using the scoop as a brake near a destination star rather than as a main engine, which eases the throttle requirements but still asks for large fields and robust control. Ideas that manipulate space-time itself appear in theory papers. The Alcubierre metric describes a warp bubble that moves space rather than the ship moving through space. Relativity is not broken because locally nothing goes faster than light. The formulation needs regions of negative energy density to shape the bubble, sometimes called exotic matter. Quantum field theory predicts effects like the Casimir force that suggest negative energies can appear in tiny, transient ways, but harnessing them to build and guide a macroscopic bubble is far beyond current understanding. Energy estimates for practical bubbles are also enormous, and controlling a bubble's edge without destroying the craft inside is not a solved problem. Wormholes are another mathematical possibility, tunnels that connect distant points. Most solutions are unstable or tiny. Keeping one open appears to require negative energy too. Many solutions also allow closed time-like curves, which brings in causality issues that physics may forbid in practice. Electromagnetic shielding returns on the engineering side. A habitat at the center of a torus antenna could produce fields that bend charged particles away, much like Earth does. Combined systems might layer modest mass shielding with fields that reduce dose further. Fields also interact with the plasma environment around the ship, which can cause arcing and unexpected forces on structures. Superconductors simplify current loads, but add cryogenic plumbing and quench protection. Designers map fault trees to ensure a single failure does not shut down protection. Economics and logistics keep pace with physics in planning. Any high-energy engine needs a fuel cycle and supply chain. If the propellant is hydrogen, you need storage that minimizes boil-off over long times. If it is a fusion pellet feed, you need precision manufacturing and a delivery system that works millions of times without jams. If the system uses nuclear reactors, you need a way to remove waste heat in space, which means large radiators that must survive micrometeoroids and thermal cycling. If the plan depends on assembling large structures in orbit, you need depots, tugs, and standardized interfaces so modules can arrive on multiple launches and fit together. Radiation risk management extends to avionics and sensors. High-energy particles flip bits in memory. A single event upset and can latch up electronics. Spacecraft use radiation-hardened parts, triple modular redundancy in logic, and error-correcting codes in memory. Detectors and cameras include shielding and annealing cycles to heal damage. Over long missions, calibration sequences track how sensors change so science data remain useful. Communication systems must operate with low signal power stretched over vast distances. High-gain antennas point precisely and sweep slowly to find Earth. Carband and optical links promise higher data rates, but demand tight pointing and clear lines of sight. Forward buffers store data through blackouts and solar conjunctions when the sun blocks the path. Onboard compression selects key features, spectral lines, interesting images, event triggers, so the craft sends the most valuable bits first. Autonomy schedules observations when the geometry is best and powers instruments in careful order to manage heat and current draw. Navigation for interstellar probes can use pulsar timing as a cosmic GPS. Millisecond pulsars send regular radio flashes. By comparing arrival times from multiple sources to a catalog, a probe can estimate its position. Star trackers give attitude. Gyros bridge the gaps between star tracker updates. Tiny cold gas or electric thrusters make adjustments. The farther a craft goes, the more these independent methods matter, because two-way tracking from Earth becomes intermittent and slow. Shielding designs adopt layered concepts. A thin bumper breaks up a fast grain into a plasma cloud. A standoff gap lets the cloud spread. A catch layer absorbs the remainder. Behind the catch layer sits the pressure vessel or instrument vault. Water tanks double as radiation blocks, placed around sleeping quarters or control bays to lower crew dose. For uncrewed probes, protected electronics vaults sit at the center of mass and benefit from every other structure in front. Materials are chosen for their behavior under impact and radiation. Aluminum for structure, Kevlar and next-generation fibers for spool resistance, polyethylene for proton shielding, and specialized foams to absorb shock. Thermal control runs through every system. In sunlight near Earth, surfaces heat quickly. In shadow, they chill. Far from the sun, deep, cold dominates. But instruments still create waste heat. Radiators sized for crews must also handle different attitudes and phases. Louvers and variable emissivity coatings help. Nuclear systems demand continuous heat rejection. Radiators cannot be stowed when power is on. Dust coatings can lower radiator performance, so designs include orientation plans and, in some cases, gentle shaking or gas puffs to clean surfaces. Life support for long trips leans on closed-loop systems. Water is recycled from humidity and waste. Carbon dioxide is removed from air and split to recover oxygen. Food production can reduce resupply, but needs light, nutrients, and careful control. Microgravity affects bones, muscles, and fluids. Artificial gravity by rotation could help, but rotating structures add mass and point to new docking and control problems. Medical systems must handle trauma, illness, and dental work without quick return. Training and telemedicine fill gaps. All of these subsystems consume power and space and must be designed for maintenance with limited tools. Planetary protection adds constraints when targets might host life. A lander for Europa or Enceladus must be cleaned to extreme standards so it does not carry microbes that could confuse results or harm native ecosystems. Cleaning hardware to that level means special materials and assembly lines, which increase cost and schedule. On return missions, sample handling and containment on Earth must be designed so that any unknown organism or chemistry cannot escape into our environment. These flows require test runs and verification by independent groups. Program structure shapes what gets built. Incremental flight tests can retire risk for parts of a system. A new sail film, a compact reactor, a long-life pump, a high-power laser phase array element. Demonstrators launch early to collect real data in space, while the full mission waits until key questions are closed. Ground facilities emulate pieces of the environment: radiation, vacuum, thermal cycles, but spaceflight often reveals couplings nobody expected. Teams treat telemetry as a science stream of its own, learning from every mode switch and every tiny drift. Near-term progress fits within tools we already understand. Nuclear thermal rockets heat hydrogen in a compact reactor and push it through a nozzle at much higher exhaust speed than chemical engines. That means less propellant for the same change in velocity, or shorter trips with the same launch mass. Nuclear electric systems pair a reactor with ion or Hall thrusters. They do not give sharp kicks. They give a steady push for months or years. The physics and engineering are known from ground tests and past electric propulsion missions. What's missing is full funding, flight qualification at scale, and the policy framework to fly nuclear stages. With those pieces in place, travel times to Mars could drop from about 9 months to roughly 3 or 4. Cargo could move on more flexible timelines. Orbiters and landers could carry thicker shielding, bigger radiators, and longer-lived instruments without breaking mass limits. Continuous thrust profiles change mission design. Chemical stages burn hard for minutes, then coast. Electric stages add speed gently the whole way. A small thrust, kept on for thousands of hours, builds large velocity change. A spacecraft can spiral outward, meet one target, then retarget for another without new propellant deliveries, as long as power and xenon, or another working fluid, hold out. Navigation shifts from a handful of major burns to many short ones. Teams watch Doppler and range data, adjust the thrust vector by fractions of a degree, and keep errors from growing. Operations become more about power budgets, thermal limits, and erosion of thruster grids than about giant engine firings. Advanced ion drives extend this approach. Gridded ion engines and Hall thrusters reach high exhaust velocity, so the propellant mass stays low even for ambitious tours. If power comes from a reactor rather than sunlight, performance does not fall off beyond Mars. A bus with tens of kilowatts could visit several Kuiper Belt objects over a decade. At hundreds of kilowatts, capture into orbit around a dwarf planet becomes realistic after a long push and a long break. The clock still runs in years, but what you can do in those years expands. Multi-encounter campaigns, adjustable altitude orbits, repeated passes over regions of interest, and revisits when lighting and geometry change. Solar sailing sits in a different niche. A sail needs no fuel, only sunlight and patience. Better films, stronger booms, and smart attitude control let small, low-cost sailcraft hold stable thrust directions. They can climb to high inclinations, hover over poles, or ride resonances that would be expensive with rockets. For missions that do not require speed, the savings are large. A stream of identical sailcraft can spread across the inner solar system, each carrying a simple instrument suite to map dust, fields, and small bodies. Farther out, sails lose push as sunlight thins, but a close pass near the sun before deployment can load them with extra speed. For interstellar ideas, gram-scale sails pushed by beamed light are being studied in labs. Turning that into practical probes means work on sail materials that survive high flux, laser or microwave arrays with precise phase control, and tracking that keeps the beam on a fast-moving target. Breakthrough physics may arrive, but plans cannot depend on it. Quantum mechanics and relativity once rewrote rules, yet spacecraft performance usually improves through materials, power density, thermal control, and higher exhaust velocity. Program baselines assume conservative growth, better reactor-specific power, longer thruster life, higher temperature radiators, and lighter structures. If a true leap appears, compact fusion, new superconductors, or a way to couple to the vacuum for thrust without propellant, it will slot into tested architectures only after independent proof and space qualification. Likely speed limits over the next century separate by payload type. Uncrewed probes that accept long cruises and higher acceleration could reach a few % of light speed with nuclear pulse or advanced fusion concepts if those systems mature. That still yields decades to the nearest stars. Human-rated craft will sit lower, well under 1% of light speed, because of shielding, life support, and acceptable acceleration. Within the Sun's family, that band supports robust exploration. Between stars, it supports flybys and long baseline measurements rather than arrivals that stop and orbit. Purpose sets the envelope. Robots do not need gravity, food, or sleep. They can ride high G-loads during brief burns, hibernate for years, and wake on timers. They need power, thermal control, fault tolerance, and a communication plan that survives blackouts. Human crews need pressurized volume, water and air recycling, radiation protection, medical gear, exercise systems, and shielding against flares. Redundancy and maintainability add mass. Every kilogram devoted to human support is a kilogram not available for propellant. For multi-year voyages, spares and tools pile up because you must fix what breaks far from home. Generation ship ideas push demands even farther. A closed ecosystem must recycle air and water at high efficiency for centuries. Food production needs area, lighting, and nutrients. Healthcare must handle emergencies without evacuation. Education and governance must keep skills and safety culture intact. Those are engineering inputs, not side notes. They turn a vehicle into a town with power, waste, and community systems that cannot pause. Robotic exploration will move first. Machines scout resources, measure radiation, map fields and dust, and test navigation methods. If the data show a clear case, crews can follow with clearer risk models. Target choice evolves as telescopes improve. Proxima b can be probed from Earth and near-Earth telescopes for mass, orbit, and atmospheric gases. A local probe could sample charged particles, dust, and magnetic fields in situ, measure winds and escape rates directly, and image surface structure at scales telescopes cannot reach. That gap remains large even as remote instruments improve. Whether to launch now or wait is a recurring question. If technology accelerates fast enough, a later, faster craft can overtake an earlier, slower one and arrive first. If progress is incremental, waiting just means losing years of data. The practical path uses measured trends: power per kilogram, radiator performance, thruster lifetime, link margin at distance, and the cost to put a kilogram into deep space. When those curves flatten, it's time to launch. When they rise sharply, you hold and invest on the ground. Many programs split the risk. A Pathfinder flies soon with modest goals, while a flagship waits on one or two enabling technologies to clear thresholds. Historical examples show why windows matter. The Voyagers flew with 1,970 seconds computers because a rare alignment offered gravity assists to 4 giant planets. Delaying for better hardware would have missed that geometry. The lesson is not to launch everything quickly, but to line up sky windows with technology windows and to lock schedules to both. Speed bands define practical action. Launchers place payloads into low Earth orbit near 17,000 miles per hour. Burns to other planets push that into tens of thousands. Electric propulsion can add hundreds to thousands more over months. Sails can add speed close to the sun and then coast. Nuclear pulse or advanced fusion, if proven, could push small probes to 1 or 2% of light speed. These numbers follow from exhaust velocity, power density, radiator size, and shielding mass. Each step calls for new ground facilities, flight demos, and careful qualification. Within these bands, the solar system is reachable on human timescales. Lunar bases and Mars crews can rotate on multi-year cycles. Outer planet orbiters cruise for most of a decade, then operate for another. Sample return chains use multiple launches, depots, and tugs to bring grams to kilograms back. Kuiper Belt tours stack encounters. Interstellar work stays on century tracks, unless engines change scale. Data systems must store and share results across generations, so knowledge does not depend on any single team. Infrastructure makes missions repeatable. Electric tugs move cargo between orbits. Depots manage cryogenic propellants with insulation and active cooling. Standard docking rings and data buses let new modules fit old ones. Radiation test beds in high orbit expose materials and electronics for years. Nuclear thermal flight tests prove reactor behavior above the atmosphere and check exhaust handling. Microwave or laser ranges validate beam control for beamed energy trials. Each asset reduces risk for the next mission and allows alternate routes when one element fails. Automation grows in scope. Onboard planners schedule instruments around power and thermal constraints. Fault management isolates bad sensors and switches to backups. Vision-based navigation aids landing and proximity work. Compression adapts to scene content so quiet frames do not flood the downlink. Long cruise health monitoring predicts failures before they stop a mission. Ground control shifts from direct piloting to supervising, updating goals, and reviewing data. Economics favor common buses and modular payloads. When the same thruster, reactor, radiator, avionics stack, and software fly many times, suppliers improve yield, costs come down, and reliability climbs. Missions can then spend on new instruments rather than on reinventing platforms. A steady cadence builds the workforce and tooling needed for larger steps. Higher power reactors, larger sails, longer life engines, and higher data rates. Risk is managed with design features, not slogans. Radiation dose is cut with shielding, storm shelters, and shorter transit times. Micrometeoroid risk to radiators is handled with segmentation and isolation. Fire risk in cabins is reduced with materials that resist ignition and with compartments that can be sealed. Software risk is controlled by redundancy, watchdogs, and independent verification. Navigation risk is bounded by early correction windows and by cold gas reserves held for late trims. Training follows the hardware. Crews practice maintenance, medical procedures, geology, docking, and systems diagnostics. Ground teams rehearse anomalies with hardware, in the loop, and realistic communication delays. Autonomy is tested in off-nominal cases to map decision trees. Mission rules are written in plain language and matched to software logic so both interpret states the same way. As launch costs drop with reusability and rideshare, many small missions can fly. A fleet of compact orbiters and landers can scout a target world before a flagship arrives. Distributed sensors can record weather, dust, and radiation in parallel and provide context for high-value measurements. In deep space, small relays can raise data rates for a main craft that would otherwise trickle data home. Funding models matter, but the technical work defines the lane. Nuclear thermal stages require reactor development, materials that survive hot hydrogen, and ground test stands. Nuclear electric flights require high-power arrays or compact reactors power processing units, and thrusters that last tens of thousands of hours. Sails require films with low areal density, coatings that survive ultraviolet and particles, and booms that deploy cleanly. Beamed energy trials require phased arrays with tight control and metrology to keep beams coherent. Fusion concepts require drivers, pellet fabrication, magnetic nozzles, and radiators sized to reject waste heat at high temperatures. Exotic ideas remain on the research side. Antimatter needs practical production and storage far beyond tiny laboratory traps. Ramjets need magnetic scoops so large that drag dominates at low speed. Warp metrics and wormholes require negative energy densities and control of space-time that modern experiments do not yet approach. These topics stay in theory and small-scale tests, while flight programs focus on engines and power systems that engineers can build, test, and certify. Robots will go first, then crews where returns justify added systems. Each step builds on the last, using proven buses, shared interfaces, and ground infrastructure that spreads cost. The governing terms do not change. Delta V budgets, power per kilogram, radiator area, shielding thickness, link margin, thruster lifetime, and navigation error growth define plans and schedules. A far future audience may see our time as the first workable steps of a spacefaring culture. That view is guesswork. What is clear is the practical work happening now. Robots cross interplanetary space. Telescopes measure faint light from early galaxies. Crews live in orbit for months. Speeds remain modest by cosmic standards, yet they are enough to place instruments where they need to be and to return long streams of data. The point is not style or hype. The point is steady capability that moves hardware, takes measurements, and improves the next design. Voyager 1 and Voyager 2 are good markers. Each carries a gold record with simple images and sounds, greetings in many languages, and basic maps. These objects will last for a very long time in cold space. The spacecraft run near 38,000 miles per hour, which is fast compared to airplanes and bullets, slow compared to the scale between stars. They will spend tens of thousands of years crossing local interstellar distances. The message is not a promise of reply. It is a durable sample of who made and launched them. The technical side is as important. Radio systems still lock to the faint carrier. Power from radioisotopes still runs heaters and instruments. Error-correcting codes still carry bits through noise. Parker Solar Probe shows a different axis of speed. By falling close to the Sun and using Venus flybys, the probe reaches about 430,000 miles per hour, near perihelion. That number does not change the problem of interstellar distance, but it enables in situ measurements of the solar wind, magnetic fields, and dust near the star. Heat shields, thermal blankets, and careful pointing keep instruments within limits, while the outer shell takes the heat load. The record speed is not an end. It is the result of a design tuned for a hard environment. Space budgets and opportunity cost come up often. The scale sounds large in isolation, but compared to national and global spending, the fraction is small. A typical year of civil space work funds weather satellites that protect lives and property, navigation systems that support transport and power grids, climate measurements that guide policy, and communications that link remote areas. Hardware and software built for space often find uses on the ground. Imaging sensors, lightweight materials, data compression, water recovery systems, radiation-hardened electronics. Missions that move slowly still force progress because they must work for years with tight margins. So every watt saved and every gram removed shows up later in medical devices, aviation, energy systems, and computing. Risk to a single planet species is another driver. A permanent outpost on the Moon or Mars is not escape fiction. It is risk diversification. A second site with independent power, water processing, and food production lowers the chance that one event will halt all human activity. Speed limits do not erase that value. A supply chain that tolerates months-long transit can still build radio networks, labs, habitats, and greenhouses, then grow better cycles as engines and power improve. The search for life sets concrete missions. In the near term, this means drilling and chemistry on Mars, plume sampling at Enceladus, radar sounding and mass spectrometry at Europa, and long-lived landers and aircraft at Titan. For exoplanets, it means telescopes that can separate starlight from planet light and read gases like oxygen, methane, carbon dioxide, and water vapor. None of these steps needs near light speed. They need clean optics, precise pointing, stable power, low noise detectors, and long observation baselines. A single confirmed biosignature, even microbial, would change many plans. The work is patient and specific. Sample handling that avoids contamination, instruments that can detect parts per billion, and data analysis that can separate biology from chemistry and geology. Persistence is the working model. Spacecraft that last beyond their design lives deliver large returns because calibration is known and teams learn how to nurse aging parts. Opportunity drove on Mars for roughly 15 years. Hubble has observed for more than 30 years with upgrades. Voyagers have crossed the termination shock and kept reporting. Longevity depends on fault protection, low vibration, thermal stability, and thorough ground testing. Speed does not replace those. It sits alongside them as one parameter. Looking a century ahead, speed ranges still depend on payload type and power source. Uncrewed probes that accept high acceleration can use electric propulsion for years, adding velocity bit by bit. If nuclear electric stages or compact fusion power become available, a few % of light speed for small probes moves from paper to engineering study, with cruise times that fit within multiple decades rather than millennia. Human missions keep to lower fractions because of dose limits, life support mass, and acceptable G-loads. This keeps exploration within the Sun's family and limits interstellar work to instruments without crews. Purpose separates designs. A robotic craft needs power, thermal control, radiation tolerance, onboard autonomy, and a path to return data. It can spin for stability, endure cold, and wait through conjunctions when the sun blocks radio paths. A crewed craft adds pressure shells, air and water recycling, waste handling, medical gear, exercise machines, and storm shelters. Shielding mass grows with mission length. Structures handle loads from docking, burns, and rotation if artificial gravity is used. Spares and tools fill lockers. Every design review measures what those needs do to propellant mass, engine choice, radiator area, and comm hardware. Generation ships turn into moving settlements. Closed loops must recycle nearly everything. Lighting systems must run with stable spectra for crops. Pollination, pest control, and nutrient cycles must be controlled. Gene banks and seed reserves must be managed. Governance, training, and education become as critical as power and thrust. None of these items reduce to a single engine pick. They build a wide ledger of mass, power, heat, and reliability that shapes every other choice. Telescopes guide where to go. Proxima b and similar worlds already show up in radial velocity data and sometimes in transits. Direct imaging and high-resolution spectroscopy will supply air composition, cloud properties, and temperature maps from light curves. A local probe adds what remote sensing cannot: particle environments, dust populations, small body dynamics, close imaging of surfaces, and changes over time at scales too fine for a telescope. A clear value case is a nearby system with strong biosignature hints. Without that, scouting focuses on our own moons and small bodies where payload mass buys direct sampling. Launch now or wait is solved by tracking actual trends. If power per kilogram on orbit grows slowly and thruster life is already beyond the mission's need, waiting offers little. If a single technology is moving rapidly, for example, stable large mirrors or low-mass radiators, missions dependent on that part may hold. Many teams split risk by flying a pathfinder with narrow goals and a flagship later when the key part has been proven in space. Engineering sets speed bands. Launches reach low Earth orbit at about 17,000 miles per hour. Trans-Mars and outer planet injections add tens of thousands more. Electric propulsion can add hundreds to thousands over months and years. Solar sails can add near the sun and then coast. Beamed sails for gram-scale craft could reach much higher fractions if arrays and sails are built to spec. Nuclear pulse or fusion concepts, if shown to be practical, could move small probes at 1% or 2% of light speed. Each band ties to exhaust velocity, power density, heat rejection, and allowed dose. Within those bands, the solar system is accessible on human schedules. Lunar logistics can use reusable landers and tugs. Mars transfer stages can run on synod windows every 26 months. Outer planet orbiters cruise 7 to 10 years, then work for many more. Sample return builds chains, ascent vehicles, capture in Mars orbit, Earth entry capsules, and biosecure labs on the ground. Deep surveys of the Kuiper Belt time encounters to lighting and geometry to maximize mapping. Across it all, operations rely on tracking, link margins, and planned safing rules that handle faults without losing vehicles. Infrastructure reduces risk and spreads cost. Cryogenic depots with active cooling limit boil off. Modular standards let tugs, habitats, landers, and cargo connect without custom adapters. Radiation test beds in high orbits expose materials and electronics so lifetime can be predicted. Nuclear thermal tests above the atmosphere verify fuel elements, turbomachinery, and nozzle erosion under real flow. Beamed energy trials measure phasing, pointing, and sail stability. Each success turns one more unknown into a known on the next mission's risk chart. Automation scales with distance and delay. Onboard planners sequence instruments around power and thermal budgets. Fault management detects outliers, isolates failures, and reconfigures. Autonomous navigation uses vision and LiDAR to hazard avoid on descent. Compression and prioritization send the most valuable data first when downlink is tight. Health monitoring projects component wear so maintenance can be scheduled. Ground teams move from hand-holding to supervision and parameter updates. Economies of repetition matter. Common buses and avionics stacks shorten development. Flight-proven thrusters with known erosion rates simplify life testing. Standard power processing units, valves, and thermal hardware build a parts library. Training improves, as crews and operators use the same tools across missions, insurance, and schedule risk drop. Larger steps, higher specific impulse, bigger arrays, longer life engines then sit on a stable base. Risk controls are specific. Doses cut with water walls and polyethylene, with storm shelters wrapped around sleeping areas and workstations. Radiators are segmented, so a puncture does not drain a whole loop. Fire risk is lowered with low flame materials and compartments that isolate. Software is protected by redundancy, watchdogs, and independent verification. Navigation risk is kept down with early correction windows and cold gas reserves for late trims. Debris and dust risk is handled with Whipple shields, leading ice or water tanks, and pointing rules during cruise. Training follows design. Crews drill on maintenance, medical care, docking, EVA, geology, and failure modes. Ground control rehearses anomalies with hardware in the loop and simulated delays. Autonomy is tested on edge cases, not just nominal paths. Mission rules are written in plain language and matched to code so interpretations align. Checklists and timelines update with real telemetry, not just with plan assumptions. Launch cost trends open room for fleets. Rideshare fills boosters with small probes. Constellations scout targets before a flagship commits. Shadowcraft serve as relays to raise data rates and to provide geometry for tomography or radio occultations. Distributed sensors build context. Weather on Titan, dust at Mars, radiation at Jupiter, plasma near the Sunday. Each unit is simple. Together, they map a complex field that a single platform would miss. Cultural and educational effects are measurable. Images from Hubble and Webb enter classrooms and labs. They also set requirements for next-generation instruments. Earth imagery from low orbit teaches how storms build and how forests change. It also validates climate models. None of this needs high cruise speed. It needs platform stability, calibration, careful data handling, and open archives. Speed numbers that matter today are straightforward. Uncrewed probes can reach hundreds of thousands of miles per hour when they fall inward and trade altitude for kinetic energy. Cruise speeds across the outer system sit lower but persist for years. Human missions beyond Earth orbit still take tens of thousands of miles per hour in transits and then brake for capture or landing. Electric propulsion adds speed continuously rather than in bursts. Nuclear pulse or fusion drives, if built and tested, extend the range by major steps for small payloads. In every case, capture at the destination costs delta V. Braking is not optional if you plan to orbit or land. Physics sets non-negotiable boundaries. Light, speed limits, signals, and travel. Energy must be provided and rejected as heat. Mass resists acceleration. Radiation accumulates over time and varies by region and event. Dust and micrometeoroids are rare, but damaging at high relative speed. Communications spread out with distance. Link margin depends on antenna gain, transmitter power, wavelength, and pointing. Trajectories depend on geometry and gravity and must be planned to match moving targets. Design choices follow those limits through delta V budgets, power density, radiator area, shielding thickness, link margin, and navigation error growth. To see how we reach today's speeds, it helps to trace the path from first orbit to deep space. In 1957, Sputnik 1 circled Earth at about 18,000 miles per hour, fast enough to stay in orbit, not fast enough to escape. 4 years later, Yuri Gagarin flew at similar orbital speed. Those flights proved we could climb off the pad and stay up. The next jump required more. Earth's escape velocity is about 25,000 miles per hour, and the Apollo missions had to hit that number and hold a similar pace during the coast to the Moon. Crews crossed cislunar space in about 3 days at speeds that, for the first time, truly left Earth's grasp. The shift was not just altitude, it was regime. After Apollo, human flight turned inward. The space shuttle reached low Earth orbit at about 17,500 miles per hour, slower than Apollo's translunar pace, because the goal changed. The shuttle was a truck and a workshop. Deploy satellites, retrieve them, build the International Space Station. For 3 decades, crewed missions stayed close, trading speed for reuse, cargo, and construction. Meanwhile, uncrewed craft pushed limits in other ways. The Helios probes fell deep toward the Sun in the 1,970 seconds and hit roughly 157,000 miles per hour at perihelion. Voyager 1 and 2 used gravity assists to climb to interstellar trajectories, with cruise speeds near 38,000 miles per hour relative to the Sunday. The method mattered as much as the numbers. Gravity assists add speed without hauling huge propellant tanks, but only for light, uncrewed payloads, and only along paths the planets allow. Ion propulsion brought a different improvement. Instead of burning propellant in minutes, ion engines accelerate ions with electricity and can run for thousands of hours. Deep Space One proved the basics in 1998. Dawn turned the concept into a tour by visiting Vesta and Ceres in one mission, something chemical rockets could not do with a single launch. The price was patience. Dawn took years to spiral outward, and then years more to reshape its orbit for the second target. Electric propulsion raised efficiency, not peak speed, and it traded bursts for steady push. A pattern emerges. The 1,960 seconds delivered a rapid climb. First orbit, first escape, first lunar surface. Later decades delivered careful gains, better instruments, longer lives, smarter navigation, higher exhaust velocity, and thicker science returns per kilogram. Chemical and electric propulsion approach practical limits set by exhaust speed, power density, and heat rejection. The next step likely needs nuclear stages, thermal or electric, or, farther out, fusion. Even then, the increase is measured in factors of a few, not orders of magnitude. Long-duration missions expose gaps beyond engines. Life support on the International Space Station recycles much of its water and some oxygen. Yet food, spare parts, and other consumables come up on resupply craft. A Mars transfer can carry everything needed for months. A journey lasting many years cannot. It must close loops for air, water, and food, with very small losses. Tests on Earth show how hard that is. Biosphere 2 sealed 8 people inside a 3.14-acre structure in Arizona with linked ecosystems. Oxygen dropped as concrete absorbed gases. Carbon dioxide spiked. Many species died. Human factors frayed. The experiment ended early. Lessons came from the data, but the result underlined how sensitive a closed system can be. Losses that seem small grow over time. A 1% annual leak in a water loop empties the tank over a century. Trace contaminants accumulate. Filters fill. Microbes shift populations. Pumps wear. Valves stick. Every part needs diagnostics and maintenance plans that work without a warehouse next door. Spare parts add mass. Mass raises propellant. Propellant complicates tanks and insulation. Tanks and insulation add more mass. The loop is not only biological, it is mechanical and logistical. and it ties back to propulsion. Human psychology brings its own constraints. Data from submarines, Antarctic stations, and orbital crews show people adapt for months. Then stress climbs, sleep patterns shift, conflicts rise, attention drifts. The ISS operates with crew rotations and steady contact with Earth. A Mars crew would spend 2 to 3 years largely without rescue, with communication delays of minutes. A generation ship would remove rotations and quick support entirely. We do not have direct data for lifelong confinement in a small, artificial world. People born there might adapt to the only environment they know, but development, education, and culture would unfold under shipboard limits, not Earth's variety. Planning must assume unknowns in behavior, not just in hardware. Ethics and governance are not side notes. A multi-generation mission binds people who were never asked. History on Earth shows that cultures change in decades. Empires and alliances rise and fall in less time than an interstellar cruise at attainable speed. Proposals range from strict charters to flexible democracies. Both face the same point. Crews may revise goals, halt, or turn if conditions or views change. At interstellar speeds, turning is not a casual act. A 1-degree course change after years of acceleration demands a large sideways velocity change and a matching propellant budget. The guidance system must keep errors small from the start, so those budgets stay within what the vehicle can carry. The historical record also shows value in slow accumulation. Hubble's decades in orbit produced calibrated, stable datasets across many instruments, enabling discoveries that a quick flyby cannot match. Long-lived Mars rovers mapped seasonal cycles and dust patterns that short missions would miss. Voyager's long baseline let scientists study the heliosphere's boundary in a way no near-Earth spacecraft could. Each of these missions stayed within modest speeds but demanded strong engineering in power, thermal control, radiation tolerance, and autonomy. Reliability was the multiplier. Speed records still teach. Helios and Parker show what falling toward the sun can provide. High local speeds that unlock measurements near the star, at the cost of extreme heat loads and strict pointing rules. Gravity assists show how to trade momentum with planets within windows that repeat only on long cycles. Ion propulsion shows how many small pushes can rearrange orbits over years. None of these erase the basic constraint that you must also slow down to orbit or land at the destination. Delta V for capture is part of the budget from day one. Looking back, progress has combined bursts and plateaus, early flights, solved launch, staging, guidance, and re-entry. Apollo added deep space navigation, high-energy flight, and life support for trips measured in days. The shuttle and ISS period refined operations, construction in orbit, and international logistics, uncrewed missions, extended communication links, radiation design, and autonomy, while probing farther out. Ion engines, aerocapture research, high-temperature materials, and radioisotope and solar power systems improved margins. Each gain fed the next plan, even when top speed stayed similar. The limits that persist are not management slogans, they are physics. Exhaust velocity sets how efficiently propellant turns into delta V. Power per kilogram sets how strong electric propulsion can be and how large radiators must be to dump waste heat. Radiation and dust set shielding thickness and placement for crews and electronics. Communication delay sets autonomy requirements. Navigation error growth sets how early course corrections must be made. These items appear in every review, whether the target is lunar orbit, the Kuiper Belt, or interstellar space. Future steps in speed will likely come from higher exhaust velocities and higher specific power. Nuclear thermal stages heat hydrogen to temperatures chemical combustion cannot reach, doubling effective exhaust speed. Nuclear electric stages supply steady power to ion or Hall thrusters beyond the range of sunlight, enabling long pushes and complex tours. Fusion, if made practical for propulsion, could raise exhaust speed into the percent of light range for small probes. Beamed energy sails shift the heavy power source off the vehicle for acceleration, with the trade that braking needs another system at the destination or a magnetic sail to interact with the target star's wind. Even with better engines, mission design remains the balance between speed, mass, and arrival conditions. Fast transits reduce radiation dose and crew time in microgravity, but arrive hot and demand large braking budgets. Slower paths save capture propellant and simplify insertion at the cost of more exposure and longer operations. The right answer depends on payload, target, and acceptable risk. That is how the field arrived at today's speeds, and why the next increases will be measured against the same tables of delta V, link margin, heat rejection, shielding mass, and the fuel required to change course once underway. Space navigation starts with a simple fact: nothing stands still. Earth circles the sun orbits the galaxy, and stars drift across the sky. There is no fixed signpost. On Earth, GPS, maps, and landmarks give a stable frame. In space, you aim not at where a world is today, but where it will be when you arrive. A Mars transfer launched in summer might intercept Mars months later at a point millions of miles from where Mars sat at liftoff. Hitting that moving target means solving orbital geometry with high precision and keeping small errors from growing. The math behind this is the n-body problem. For two bodies, say, the Sun and a spacecraft, the solution is clean. Add a third body, and the paths become sensitive to starting conditions. Add Jupiter, Saturn, Earth, Mars, the Moon, and the rest, and you need constant computation. Mission teams run high-fidelity models on Earth, then update using tracking. Doppler shift in the radio link gives speed along the line of sight. Range timing gives distance, and angle measurements refine direction. Spacecraft carry star trackers, small cameras that match star patterns to a catalog to fix attitude, and gyroscopes to measure rotation between star fixes. Farther out, communication delays stretch, so more navigation must be done on board, using these sensors and simple burns early in flight when small nudges have the biggest effect. Interstellar navigation scales the same ideas to longer times. Stars have proper motion. Their positions change by arc-seconds per year. Proxima Centauri sits about 4.24 light-years away now, but it does not wait. Over tens of thousands of years, its position shifts by a measurable fraction of a light-year. A trajectory error of 1,000th of a degree, barely visible, becomes a miss by billions of miles at arrival. Big course changes late in cruise are not realistic. The delta V cost grows with speed. So the aim must be set with star catalogs that include proper motions, radial velocities, and gravitational influences, and those catalogs must be tied to the probe's clock and sensors for updates without constant help from Earth. At higher fractions of light speed, relativity adds corrections. Time on the spacecraft runs a little slower than time on Earth. Clocks must be synchronized with models that include time dilation. Light from stars ahead is blue shifted. Light from behind is red shifted. The sky seems to crowd toward the direction of travel in a visual effect called aberration. Sensors must calibrate against these changes, so star trackers do not misidentify patterns. The cosmic microwave background would appear warmer ahead and cooler behind, which affects long-wavelength instruments. The physics is known, but we have not yet flown navigation that accounts for these effects at mission scale. So any design must include margins, test modes, and cross-checks. A practical stepping stone is an interstellar precursor, a mission to hundreds of astronomical units, AU, not light years. The Sun's gravity behaves like a lens at about 550 AU and beyond. Light from a distant target, such as an exoplanet, can focus along a line opposite the target behind the sunday. A spacecraft placed on that line could sample the focused light and reconstruct images at resolutions far beyond a normal telescope. Voyager's cruise speed would take about 8 decades to reach 550 AU. With nuclear, electric, or optimized sail trajectories, a carefully designed probe might arrive in a few tens of years. That timeline fits a career if started early, and gives science returns that cannot be produced closer in. Such a mission tests key systems. Autonomous navigation must handle long gaps and faint signals. Power must last for decades, likely with radioisotope sources or advanced reactors. Thermal control must work through deep cold. High-gain antennas or optical comms must close links over vast distances with tight pointing. If biological experiments are included, closed-loop subsystems can be run and monitored at scale, though for initial flights, keeping payloads uncrewed and simple lowers risk. Each precursor refines propulsion, navigation, and communications for longer attempts. Payload choice for true interstellar probes drives architecture. Encoded messages like the Voyager records assume a finder can decode physical signals. Digital payloads assume compatible logic. A chemistry-based message, DNA segments, plus a how-to-read guide is more universal in principle, but it still assumes shared biochemistry. A flexible option is an artificial intelligence probe. No life support, no supplies, higher tolerance for acceleration and radiation, and the ability to analyze locally and compress results. With self-replication, one probe could build copies using local materials and fan out. That lowers launch mass, shortens intervals between discoveries, and multiplies coverage. Self-replication raises control risks. If a replicator misreads rules, it could copy without limits or alter itself in ways that drift from original goals. Safeguards must be baked in. Limited replication counts, cryptographic identity, resource quotas, kill switch protocols, and narrow task sets tied to verifiable objectives. Interaction rules matter too. Transmission etiquette, beacon power limits, and clear signatures that identify the probe's origin and purpose. Aligning behavior over centuries requires verification methods that do not depend on Earth's real-time oversight. Speed limits reframe the Fermi paradox. A galaxy 100,000 light-years across takes 1 million years to cross at 10% light speed. Colonization is not a single wave. It is steps. Establish, build, reproduce capability, then depart again. The total time to fill the disk could run to tens of millions of years, still small compared to the age of the galaxy, but large compared to the lifespan of technologies or cultures. If intelligent life is rare, there may not have been enough starting points or time for wide coverage. In that case, radio silence reflects sparse origins and slow front speeds rather than absence. Another angle supposes faster-than-light methods. Relativity tests from particle accelerators to pulsar timing support light speed as a limit for signals and matter. Hypothetical exceptions require negative energy densities or space-time engineering we cannot realize. Treating FTL as an assumption solves the paradox on paper but removes the constraint that guides real designs. A different answer is the filter. Many civilizations end themselves before building persistent interstellar systems. In that view, the silence is survival bias. Navigation, propulsion, and communication plans still matter, but so do social resilience and hazard management. Interstellar navigation also has to handle dust and gas. A probe at a few % of light speed meets a thin medium, mostly hydrogen, at dangerous energies. Whipple shields put thin bumpers ahead of the main hull to vaporize grains, then catch the plasma cloud with a standoff layer. Ice or water tanks can serve as sacrificial mass in front. Charged particle deflection with magnetic fields helps for ions, but most dust is neutral. Forward sensors help little because closing speeds are too high. By the time you see a grain, it is already at the shield. So design assumes random hits and sizes the shield and spacing to keep expected damage within limits. Course knowledge comes from multiple references. Star trackers give attitude. Pulsar timing can give position by comparing pulse arrival times from several known pulsars to a catalog. Optical navigation measures known stars and background galaxies to check drift. Onboard clocks keep time over long gaps with stability, high enough to support dead reckoning between updates. Propulsion events are modeled so the system knows the delta V achieved versus commanded, feeding back into the estimator. These loops must function without ground in the loop and must be robust to sensor outages and mode changes after safe mode events. Communication over interstellar distances rides narrow beams. Radio dishes with very high gain or optical terminals with tight lasers reduce required transmit power but demand fine pointing. Faint signals arrive at Earth, spread over large collecting areas, and must be integrated over long periods. Data pipelines prioritize compressed science first and housekeeping later, with fault logs preserved to reconstruct anomalies months after they occur. Clock drift and relativistic effects are corrected in the link budget, so bit error rates stay within code limits. Interstellar precursor craft can carry technology demos that matter later. Cold atom clocks for precision timing, deep space optical comms, long-life power processing units for high ISP thrusters, sail materials that hold shape near the sun, and radiation-tolerant computing with error correction that handles decades of cumulative dose. Each item reduces uncertainty in navigation models and increases confidence that small burns will produce the intended vector change after years of drift. Ethical planning intersects with navigation when missions include replication or persistent presence. Safe operating envelopes must be defined in coordinates and time, where replication is allowed, where it is forbidden, beacon power levels, frequency bands reserved for discovery versus housekeeping, and rules for shutting down on detection of biosignatures or other technosignatures. These rules must be embedded in firmware that is auditable and hard to alter, with proofs that decision trees lead to defined outcomes under specified inputs. The practical path from today to these missions is staged. Build star catalogs with better proper motions. Fly deep space clocks with drift low enough for autonomous timing. Demonstrate optical navigation and optical comms at tens to hundreds of AU. Validate pulsar-based positioning in flight. Test long-duration electric propulsion with known erosion rates and measured thrust noise. Characterize shield performance with hypervelocity impact tests and in-flight monitoring of crater rates. Each result feeds the next estimator and reduces the uncertainty margins designers must carry. Relativistic time dilation changes the clock, not the distance. At about 90% of light speed, a traveler's onboard time runs around 44%. as fast as time on Earth. A 10-light-year trip that takes roughly 11 years by Earth's clock would feel like about 5 years on the ship. Push to 99%, and the same trip is a little over a year and change of ship time. At 99.9% months, the view ahead blue shifts, the view behind red shifts, and onboard clocks drift relative to clocks at home. The catch is energy. Getting a vehicle with real mass near light speed needs energy on the order of its rest mass multiplied many times. Even with perfect matter to antimatter conversion, the fuel mass grows steeply because the rocket must push its own propellant. A 1,000-ton craft, needing tens of thousands of tons worth of kinetic energy, turns into a stack dominated by fuel, tanks, and shielding before you include habitat, power, and radiators. With our current fractions of a percent of light speed, time dilation is a textbook effect rather than a mission tool. Funding and incentives shape how fast we progress. Nations fund space for security, prestige, science, weather and communications, and industry. Big leaps, like Apollo, rode geopolitical competition that unlocked budgets far beyond pure science cases. Today's large programs must compete with health, infrastructure, and defense. Crewed work in low Earth orbit and lunar return efforts absorb steady funds. Long-range propulsion research competes for what remains. A fusion or nuclear pulse engine program would span decades and cost in the hundreds of billions. The near-term payoff is faster Mars cargo, richer outer planet tours, and interstellar precursors. The far-term payoff is small probes at a few percent of light speed. Whether that clears political thresholds depends on coalitions that can survive election cycles and budget swings. Private launch has altered access by lowering cost to orbit and raising flight cadence. Commercial operators invest where revenue exists. Satellites, broadband, imaging, crew and cargo to stations, and future in-space manufacturing. Interstellar work, generation ships, and high-risk propulsion prototypes lack direct markets. Historically, governments carried those costs. Then industry scaled the pieces that proved useful. If public investment retreats while private capital follows profit alone, the path to high-specific impulse engines, deep space reactors, and beam arrays narrows. Hybrid models help. Public-private partnerships for test stands, power processing units, radiators, high-power electric thrusters, and flight demos that de-risk the next step for everyone. International programs spread risk and cost. The ISS showed that shared planning, common interfaces, and standing logistics chains can operate for decades. A fusion propulsion testbed or a beamed sail array could follow a similar pattern. Many nations contribute modules power, phasing electronics, mirrors, tracking, and all get data. The challenge is governance over time. Legal frameworks must define export controls, liability, data rights, and debris mitigation, while budgets pass through parliaments that change hands. Long program plans need off-ramps, phased milestones, and clear technical gates, so contributions stay aligned when politics shift. Generation ships sit in the realm of engineering systems that include society. Size is not decoration. Volume sets air, water, crops, workshops, and storage. Population size sets genetic diversity and duty cycles for training, maintenance, and care. Food production needs light, nutrients, pollination, and pest control in closed rooms with finite spares. Water and air loops must close with near zero loss. Materials must recycle at scale. Metals, plastics, organics. Power must be continuous, with safe redundancy. Every loop adds sensors, pumps, filters, and software that must run for centuries, with maintenance by people born after launch. Ecology becomes an engineered graph. Choose crops, microbes, insects, and decomposers for stability, calorie yield, micronutrients, and resilience. Track oxygen production and CO2 uptake as seasons and diets change. Design buffers for shocks, reserve seeds, backup cultures, quarantine protocols, and biocides with careful use rules. Biosphere 2 showed how concrete, soil chemistry, and biology can interact in unexpected ways. On a ship, surface area is small, so transient imbalances do not average out across a continent. They show up quickly in air quality and plant health. Modeling helps, but only long integrated tests reveal slow drifts and failure modes. Governance must match constraints. Constitutions can pin mission objectives, safety rules, repair priorities, and replication limits for tools and robots. Elections can choose leaders within boundaries that protect navigation, reactor safety, and habitat integrity. Courts or councils need authority to stop harmful practices and to resolve conflicts without violence. Education systems must deliver literacy in operations, life support, first aid, electrical safety, structural inspection, and software hygiene. Archives must preserve procedures, part drawings, and reasons behind rules so drift in language and culture does not erase hard-won knowledge. Culture will change. Language shifts over centuries. Music, food, beliefs, and family structures evolve. The arriving society will not match the launching one. Mission continuity then rests on institutions and training rather than on sentiment. If future citizens vote to divert, slow, or settle early, a navigation lockout cannot physically force compliance without risking lives. Practical designs acknowledge that autonomy increases with distance and time, and that engineering must tolerate a range of acceptable choices while protecting essentials like pressure, heat rejection, and reactor moderation. Genetic engineering could lower some loads. Radiation resistance genes, altered DNA repair, or modified microbiomes might reduce shielding mass. Metabolic tweaks could lower caloric needs or vitamin synthesis dependence. Longer health span would cut training churn. Each change needs clinical proof, ethical review, and monitoring, because unintended effects can surface slowly. Engineering people to tolerate cramped spaces by reducing curiosity or dampening mood responses would lighten psychological loads but crosses ethical lines. Mission design can reduce stress with light cycles, views, varied diets, exercise, privacy, and clear work-rest patterns. Editing away discontent is a different category. Digital travelers change the payload. Radiation-hardened processors with cold spare redundancy can sleep for years, wake on schedule, and operate sensors and factories. A compact probe with additive manufacturing could print parts from local regolith, build small landers, and set up relays. If it carries uploaded minds, the question becomes continuity. A digital copy shares structure and memory at the moment of capture, but then diverges. For planning, what matters is capability, data analysis close to the target, adaptive experiment design, and compression that preserves the most informative pieces for the slow link home. For safety, constraints limit, replication count, resource use, and modification of core goals. Without proofs, and checks. Relativistic navigation stacks predictable corrections on top of classical ones. Aberration shifts star positions forward by a known angle that grows with speed. Doppler shifts move spectral lines. Trackers must search for patterns in shifted bands, not just visible light. Time dilation and gravitational potential differences change clock rates. Onboard timekeeping must track these with atomic clocks and models, so dead reckoning remains accurate. The cosmic microwave background looks hotter ahead and cooler behind. Instruments must calibrate against that gradient if they use it as a reference. None of these remove the need for early, accurate course setting. They set software requirements for sensors and estimators. Precursor missions to 500-1000 AU anchor designs with real data. At the solar gravitational lens focus, the Sun acts as an enormous objective. A probe placed on the focal line of a target star can scan the Einstein ring and reconstruct an image. Requirements follow: precise ephemerides, coronagraphs to block solar glare, detectors with low noise, and metrology to keep scanning paths true. Cruise durations of 25-40 years, with nuclear electric stages or optimized sails, set power and lifetime targets for thrusters, bearings, and power processing units. Communication links over those ranges push optical terminals with tight pointing and photon counting receivers. Radio remains as backup with lower rates. Risk controls at high speed emphasize forward protection, autonomy, and conservative margins. Whipple shields stack thin bumpers and standoff layers to vaporize and spread impacts. Forward tanks of water or ice double as sacrificial mass. Magnetic fields can deflect charged particles, but not neutral dust, so both field and mass are used. Autonomy handles safing on sensor outliers, power dips, and thermal excursions, with rules that bias toward preserving attitude control and link geometry. Margins in delta V for early corrections prevent late, expensive burns. Clocks and star catalogs are cross-checked in flight, so drift is measured and not assumed. Economics drives staging. Government labs build test stands for hot hydrogen, vacuum chambers for sail films, radiation arcs for electronics, and phased arrays for beam experiments. Industry produces thrusters, tanks, valves, radiators, and avionics in repeat lots, so costs drop and quality rises. Universities run precursor instruments and data pipelines and train operators and analysts. Standards bodies define docking rings, data buses, and safety tags so modules interoperate. These pieces support faster Mars cargo, richer outer planet tours, and the first steps to multi-hundred AU science without requiring immediate interstellar craft. Specific destinations set clear speed requirements. Proxima Centauri sits about 4.24 light-years away and hosts Proxima b in the star's temperate zone. At Voyager's cruise, arrival would take on the order of 70,000 years, with an optimistic nuclear pulse stage reaching to 3% of light speed. Flight time drops to roughly 140 years. That is still multi-generational. Proxima's flares also complicate habitability. Frequent bursts of ultraviolet and X-ray radiation can strip atmospheres and sterilize surface layers, unless a planet has a strong magnetic field, deep ocean, or thick air. Alpha Centauri A and B are Sun-like, and only slightly farther out to 4.37 light-years. Stable orbits exist in principle, so they remain prime targets for flybys or remote sensing at close range. Tau Ceti lies to 11.9 light-years away with candidate planets. Even at 3% C, travel spans to 400 years. Within to 20 light-years, there are over 100 systems, but many are red dwarfs with activity binaries with complex dynamics, or stars without confirmed temperate planets. The map is rich, the nearby options are sparse, and distances dominate planning. Speed ties to power supply. A Dyson swarm billions to trillions of solar collectors in heliocentric orbits would harvest a large fraction of the sun's output. With that power, phased laser arrays could push light sails to high fractions of light speed or beam energy to remote electric stages. Building such a swarm implies a mature solar system economy, asteroid and Mercury-class mining, autonomous factories, radiation-hard electronics, precision formation flying, and closed supply chains outside Earth's gravity well. Mass flows on the scale of entire small planets would be required, along with traffic control, debris management, and thermal regulation for collectors. The idea is a ceiling for capability, not a near-term tool. Artificial intelligence becomes a core subsystem as distances grow. Today's probes follow timelines with onboard fault protection. Tomorrow's must plan routes, adjust experiments, and triage anomalies with limited bandwidth. An interstellar probe will run disconnected for years while light crosses the gap. Autonomy must cover navigation updates, power scheduling, thermal limits, instrument health, and science selection. Safeguards are part of the design: verifiable objectives, hard limits on mode changes, cryptographic identity, and logs that allow later audit. First contact authority is not a software footnote. Rules of engagement for transmissions, sensor use, and beacon power must be encoded, because round-trip human oversight is not available at scale. Resource use off-Earth lowers launch mass and raises effective speed. In situ resource utilization turns water, ice, and volatiles from the Moon, Mars, and asteroids into propellants and life support feedstocks. Water splits into hydrogen and oxygen for high-performance chemical stages. Water itself can feed electric thrusters or be stored as radiation shielding. Metals become trusses, tanks, and booms through additive manufacturing and casting in reduced gravity. The first refinery on an asteroid is slow and expensive. The 100th operates as standard equipment. Each depot reduces the propellant lifted from Earth, pushes practical delta-V higher for a given launch, and enables routes that include refueling and maintenance stops. Lunar staging follows from gravity math. Reaching lunar orbit or the surface takes far less energy than climbing from Earth to low orbit. A fuel plant at the Moon's poles using sunlit peaks for power and nearby cold traps for ice can feed tugs that ferry propellant to cislunar depots. Launchers working from the lunar surface deliver tanks to high orbits where deep space stages dock, refuel, and depart. Mars offers a similar step farther out. Local propellant from CO2 and water via Sabatier chemistry fills tanks for cargo or crew vehicles heading to the outer system. A mission that departs from Mars orbit with full tanks starts with lower gravity losses and can allocate more mass to shielding and instruments without exceeding stage limits. Laser-pushed sails extend this infrastructure model. A ground or orbital phased array beams power to very light sails, accelerating gram to kilogram-class probes to a notable fraction of light speed. Requirements include phase control across millions of emitters, adaptive optics, atmospheric correction for ground sites, and precise tracking. The sail must reflect without heating, survive acceleration, and maintain shape under photon pressure. Braking at the destination needs a counterpart stellar wind magnetic sails, photon braking using the target star's light, or another beam from a relay built in advance. Arrays also serve closer-in roles, beaming power to shadowed lunar sites, boosting cargo tugs, or topping up electric stages. Target selection depends on what can be measured before flight. High-contrast imaging and precision spectroscopy from near-Earth telescopes and solar gravitational lens precursors narrow candidates by atmosphere, temperature, clouds, and seasonal patterns. The better the catalog of proper motions and radial velocities, the tighter the initial aim, and the smaller the correction budgets. For nearer goals, such as the Jovian and Saturnian systems, higher ISP and depot refueling let one craft tour multiple moons with protected instruments and maintain thick shielding against radiation belts. For Kuiper belt work, continuous electric thrust enables sequenced flybys aligned to lighting and geometry, raising return per kilogram. AI decision scope must be set by design. Navigation, autonomy, runs estimators that fuse star trackers, gyros, pulsar timing, and optical nav of background galaxies. It commands tiny burns early in cruise. When micro-delta V saves large corrections later, science autonomy ranks data by novelty and compresses with content-aware methods so downlinks carry the most value per bit. Fault management isolates sensors, reconfigures power, and executes safing that preserves attitude and thermal limits. Update channels allow new models to upload when geometry permits, with rollback and quorum rules to guard against corruption. Shielding and pointing define survival at high speed. Forward, Whipple stacks, bumper, standoff, catcher spread dust impacts into plasma clouds before they reach core structure. Placing water tanks and regolith-filled panels ahead of habitats provides both radiation moderation and impact mass. Magnetic fields help deflect ions, but not neutral grains. Both systems operate together. Pointing rules keep the shielded face forward during cruise and rotate for compasses and science only when fields and models say risk is low. Sensors monitor crater rates and plume signatures to update flux estimates in flight. Communication over light-year scales needs gain and precision. Radio uses very large dishes and low-noise amplifiers. Optical links use tight beams and photon-counting detectors. Pointing stability at microradian levels keeps links closed. Time tagging accounts for relativistic rate differences so clocks stay aligned within code limits. Data handling prioritizes event triggers, spectra, and compressed imagery before housekeeping, with cold storage margins for long blackouts during conjunctions or geometry gaps. Dyson swarm energy budgets illustrate how power shifts limits. A fraction of solar output, if harnessed, supports beam power, fusion fuel cycles, and industry across many sites. Constructing and maintaining such networks requires standardized interfaces, autonomous assembly, collision avoidance protocols, and repair swarms. Thermal management becomes a first-order design variable. Collectors and emitters must dump waste heat without glowing in bands that disrupt observation or operations. Traffic rules prevent cascade collisions as populations of vehicles, depots, and habitats rise. ISRU chemistry drives practical timelines. Electrolysis splits water. Sabatier reactors combine hydrogen with carbon dioxide to make methane and water. Oxygen extraction from regolith via molten salt electrolysis supplies oxidizer for landers. Each line needs compressors, seals, pumps, heat exchangers, and catalysts designed for dust, radiation, and thermal cycling. Quality control for propellants, particulates, dissolved gases, temperature feeds into engine health. Storage adds cryocoolers and insulation to reduce boil-off. Transfer adds quick disconnects and standardized couplers that work in vacuum with gloves or robots. Economic cadence comes from repetition. Standard buses carry modular instruments. Electric tugs fly known profiles with measured erosion and lifetimes. Depots follow common docking and data buses. Training pipelines teach the same procedures, raising reliability. As cadence rises, the same launch mass buys more delta V or more payload because teams trim margins with real data, not guesswork. Within this frame, speed becomes a system output. Launch energy from Earth falls as reusability and rideshare improve. Refueling shifts mass budgets. High ISP stages expand reachable windows. Beams add momentum without onboard power. Navigation accuracy lowers correction delta V. Shielding mass and pointing rules set safe cruise limits. Target catalogs with precise proper motions shrink aim errors. Each improvement moves the practical velocity envelope without requiring a single breakthrough, and each is measurable in delta V budgets, power per kilogram, radiator area, shield aerial density, link margin, and navigation error growth. Microgravity reshapes the body fast. Without weight on bones and muscles, calcium leaches and fibers thin. Fluids shift upward, pressing on eyes. The heart and vessels idle because they no longer push against gravity. Crews counter with exercise, diet, and medical checks, yet months aloft still mean weeks of rehab on return. On a multi-year Mars mission, the concern is not only coming home, it is arriving ready to work in 1/3 gravity without injury. Tools, schedules, and training all bend around that single requirement. Step onto another world, strong enough to lift, walk, dig, and think clearly. Artificial gravity by rotation is the cleanest mitigation we know. Spin a habitat and the floor pushes back, but rotation brings trade-offs. If the radius is small, the spin rate must be high, and the Coriolis effect can make turning your head or moving your arm feel odd. Gentler spin needs a big ring or a long tethered pair of modules, both heavier and harder to build and steer. A generation ship all but requires rotation for decades of healthy living, which means large structures, which means more mass to shield and more energy to accelerate. Every fix drags a new line in the mass and power ledger. Radiation is a constant background. Solar storms come in bursts. Galactic cosmic rays arrive as solitary, high-energy bullets. Hull aluminum helps, but is not enough for a long cruise. Hydrogen-rich materials water. Polyethylene's slow-charged particles better. Magnets can bend some of what remains. Many designs wrap living quarters with tanks so water shields by day and drinks by night. That choice improves dose numbers and complicates everything else. More plumbing, more structure, more checks for leaks. Shielding is safety, and shielding is mass, and mass pushes against speed. Psychology adds another layer. Isolated crews start strong, then friction builds. Small habits grate, sleep shifts, mood dips and spikes. Most teams settle into a rhythm, some never do. For a 3-year round trip to Mars, mission design leans on careful selection, clear roles, private space, varied meals, and regular contact with home. Longer missions press for larger crews and more open volume so social life can breathe. Larger crews and volume mean more air to scrub, more water to cycle, more power to generate. People need other people. The vehicle must carry that truth. Food shifts from cargo to system as trips lengthen. Plants stabilize the air and calm the mind. They also need light, water, nutrients, pollinators, and pest control. Hydroponics and aeroponics cut mass and soil mess, yet pumps, filters, and lamps add complexity. A pest in a closed farm is not a quaint problem, it is a mission risk. Agricultural gear must fit maintenance cycles, spares lists, and power budgets that already serve life support and propulsion. The green corner of a ship is part garden, part lab, and part factory. Suspended metabolism concepts try to shrink these needs. If people could hibernate, transit could pass with little food, water, or conflict. Medicine can cool and slow bodies for hours or days during surgeries. Safe, months-long stasis is not here. Even if it arrives, muscles and bones still need load or stimulation, and waking must be safe and reliable. Cryogenic preservation pushes farther. Cells and embryos survive careful freezing and thawing. Whole bodies do not. Ice crystals tear tissue. Cryoprotectants help but introduce toxicity and uneven distribution. None of this breaks physics. All of it strains practice. Across systems, trade-offs compound. A light ship accelerates faster but leaves little room for redundancy and comfort. A heavy ship shelters and feeds its crew but asks more from engines and depots. Add artificial gravity and shielding, and propellant mass climbs. Trim propellant by refueling at depots, and you add mining and storage hardware. Navigation margins grow thinner as payload grows. There is no single bottleneck. Every subsystem tugs on the rest. History at sea offers a map. Early ocean crossings were slow and perilous, not because wind was weak, but because ships, charts, and care were young. Scurvy faded with diet, wrecks fell with better hulls and instruments, and voyages became routine without becoming much faster. Reliability, logistics, and skill did the work. Spaceflight already follows that arc. Station crews learned closed-loop habits and international schedules. Mars rovers learned to drive themselves. Voyagers taught how to run far on little power. Progress shows up as fewer surprises and clearer margins. Interstellar distances still mark a hard boundary. Even fast propulsion leaves cruise times measured in decades or centuries. There may never be a day when such trips feel common. The cost and risk could remain high, the effort multi-generational, or a new principle could open sooner paths. Planning cannot assume that gift. It must stand on what works: higher exhaust velocity, lighter structures, stronger power systems, better autonomy, and make steady use of windows when they open. Working within limits is not settling, it is design. We cannot change light speed, but we can shape trajectories, stack gravity assists, and aim precisely. We cannot erase radiation, but we can map it, shield against it, and time our routes. We cannot make weight vanish, but we can move propellant production off Earth, standardize depots and docks, and reuse hardware until the economics bend in our favor. Each gain is local. Together, they widen the lane. Microgravity countermeasures tighten with practice. Resistive exercise and centrifuges cut bone loss. Smart suits apply gentle pressure to shift fluids. Meds and light cycles stabilize sleep. Rotating testbeds validate comfort, spin rates, and layout. Radiation protocols stack. Water walls, storm shelters, and task timing tied to space weather forecasts. Agriculture packages diversify leafy greens for quick cycles, tubers for calories, legumes for protein spreading risk across crops. Psychological design leaves room for quiet, for routine, and for variety, and it treats communication links as life support for the mind. As infrastructure grows, speed becomes an effect of the system, not a single engine number. Launch from lower gravity, refuel away from Earth. Use high ISP stages for long pushes and chemical stages for captures and landings. route through depots and relays that shrink correction burns and downlink delays. Let autonomy handle the minutes, so people focus on the months. In that framework, fast enough is what closes the loop between power, mass, heat, dose, and timeline for a specific job, and then does it again next window. The picture that remains is neither bleak nor boastful. It is precise. Space changes bodies. We counter with load and time. Space is radioactive. We counter with mass, fields, and planning. Space is lonely. We counter with design that remembers people. Engines do not erase distance. Networks and patience make distance workable. We do not rush past the hard parts. We build around them until they fit. And if the pace feels slow against the stars, remember the scale of the clock we live under. A station orbiting 100 minutes at a time, a rover measuring seasons on Mars, a probe crossing the heliosphere in years. Each is a line in a long ledger. Each is motion. The universe keeps its own tempo. We move to it steadily, carefully, and, when we can, a little faster.